absorbing energy from receiving energy. So in this presentation, I will be dealing with photoelectric chapter, dual nature, radiation. So what do you mean by photoelectric effect? Metallic surfaces, when illuminated by ultraviolet radiation, electrons are emitted, and this effect is known as photoelectric effect. By absorbing energy from receiving ultraviolet radiation, the electrons in the metal state fraction of Einstein. So this is a schematic diagram of photoelectric effect.
Listen, children. So, about photoelectric effect, that is what we have to study in this chapter. Dual nature of radiation and matter. And you should know what is photoelectric effect. So, I thought of explaining it along with these videos. Then it will be more clear to you. So, here you can see for studying the photoelectric effect, this experimental setup is given. And you can see an evacuated glass tube. And here you can see two plates, evacuated, this is evacuated glass tube. And two plates, C and A, they are metallic plates. And between them, a potential difference is applied. Actually, this is something wrong. C is to be connected to negative, and A is to be connected to positive. Here some correction is there. A is connected to positive anode, A is connected to positive, C is connected to negative. And here a source of light is here, source of light. And light from this source enter through this window. This is a quartz window which will allow the light to pass through it. And that light will enter through this window and fall on this metal plate. And light, you know, light is electromagnetic waves. And every color has got its own wavelength and it has got its own energy. So if it is sunlight, all colors will be there. Or if it is a monochromatic light, that particular color will have its own wavelength. So such a radiation, any radiation, you can see, which is a monochromatic source of light, then light will enter and fall on this plate. This plate, it is a photosensitive plate. That means when light is incident, when light of suitable frequency is incident, that is very important. Not any light or not any radiation, light of suitable frequency is incident on this metal. So for a particular metal, for example, zinc plate, suppose this is zinc plate, zinc is a metal, zinc plate, or zinc plate, ultraviolet radiation, when ultraviolet radiations are incident, then electrons will be ejected from it. Suppose it is another material, lithium, sodium, etc., like that material. Then even with the visible light, it will emit electrons. Understood? So that depends upon the metal plate. So there is, for a metal plate, it requires a definite amount of energy to eject electron from its surface. So the minimum energy required for this metal to eject electron from its surface is known as work function of the metal. So what is work function? A metal requires a minimum amount of energy to eject an electron from its surface. For example, zinc, it will be different from cadmium, it will be different from other materials, sodium, lithium, or like that. Different materials, the work function is different. What is work function? The minimum energy required to eject an electron from its surface. So here, see, when the electrons are ejected from it, what will happen? Here, this is a positive plate. It is connected to positive of the battery. This plate is connected to positive of the battery. So electrons are negatively charged. when light is in, what is light? Light consists of photons. Photon means what? Photon is a packet of energy packets of energy, particles which are having energy, particles which are having energy. What is the energy of a photon? H nu. Nu is the frequency. H means what? Planck's constant. So E equal to H nu. E equal to H nu can also be written as Hc by lambda. Nu equal to C by lambda. What is C? C is the velocity of light. What is lambda? The wavelength of light. So, from this light source, light fall on this plate. When light fall means photons are incident. Photons are incident. What's the energy of photon? H nu. Hc by lambda. Okay. That photon is incident before this metal surface. What happened? It get the minimum energy to eject an electron from that surface. So, electrons are ejected. So, this metal's work function, what's work function? Minimum energy required for a metal to eject electron. And the incident energy, incident waves, incident light must have an energy equal to the work function. Then only electrons will be ejected. Understood? So, when the incident light is having an energy equal to the work function of the metal, then only the electrons will be ejected. So, this ray which is incident should have an energy, minimum energy. That is known as threshold energy. The minimum energy possessed by the incident radiation to eject an electron from a metal surface, that is known as threshold energy. So, what is the relation between threshold energy and work function? Energy we can say H nu zero. It's threshold energy H nu zero. Nu zero is the minimum. Yes.
Can you repeat Nandana?
Okay. So, what is the relation? See, once again you listen and you have to tell the answer. So, the minimum energy required for the metal to eject an electron from its surface, that is the work function. And the energy incident energy should have the minimum energy to eject an electron. That means that energy is threshold energy, and that wavelength is threshold wavelength, and that frequency is threshold frequency. Minimum frequency of the incident radiation to eject an electron from a surface. So I told you the energy is calculated, energy of a radiation is calculated by H nu or H nu zero. Nu zero is the threshold frequency. H nu zero is the energy of the incident photon. So what is the relation between work function? Work function we take a W zero. W zero. What is the relation between work function and this threshold energy of the radiation? What is the relation? I'll ask to Anakha, what is the relation? Anakha? No answer. Ashley, what is the answer? What is work function? What is work function? What is work function? Ashley, Ashley, Anasha, what is work function? What is work function? Tell. അറിയില്ലെങ്കിൽ അറിയില്ല എന്ന് പറ, അടുത്ത ആളോട് ചോദിക്കാലോ. കൃഷ്ണനുണ്ണി, വാട്ട് ഈസ് വർക്ക് ഫംഗ്ഷൻ? വാട്ട് ഈസ് വർക്ക് ഫംഗ്ഷൻ?
Minimum energy.
എനർജി മിനിമം എനർജി എന്തിന്?
electrons eject electrons
എവിടെ നിന്ന്? അല്ല പകുതി ഞാൻ പറഞ്ഞു അല്ലേ? സർഫസ് ഏതിന്റെ? കണ്ട ഓരോന്ന് ഇങ്ങനെ ചോദിക്കാം. ഏതിന്റെ
Metal.
സർഫസ്? അപ്പൊ അത് മുഴുവൻ പറഞ്ഞൂടെ? വാട്ട് ഈസ് വർക്ക് ഫംഗ്ഷൻ? ഇസ് ദ മുഴുവൻ പറഞ്ഞേ.
minimum energy required to eject electron from
Ah.
the surface of the metal.
അതാണ് ത്രെഷോൾഡ് വർക്ക് ഫംഗ്ഷൻ എന്ന് പറയുന്നത്. അടുത്ത ക്വസ്റ്റ്യൻ ചോദിക്കാം, അടുത്ത ആളോട് ചോദിക്കാം. മിനിമം എനർജി റിക്വയർഡ് ഫോർ ദ റേഡിയേഷൻ ടു ഇജക്ട് എൻ ഇലക്ട്രോൺ ഫ്രം ദ സർഫസ്. ഇസ്മായിൽ പറയൂ. മിനിമം എനർജി റിക്വയർഡ്, വാട്ട് ഈസ് ദ ഫോർമുല? മിനിമം എനർജി ഫോർ എ റേഡിയേഷൻ ടു ഇജക്ട് ഇലക്ട്രോൺ ഫ്രം എ മെറ്റൽ സർഫസ്. അതിനാണ് ത്രെഷോൾഡ് എനർജി എന്ന് പറയുന്നത്. ആ ഫ്രീക്വൻസിനാണ് ത്രെഷോൾഡ് ഫ്രീക്വൻസി എന്ന് പറയുന്നത്. അതിന്റെ ഫോർമുല ആണ്. എന്താണ് അതിന്റെ ഫോർമുല? മിനിമം എനർജി ഓഫ് ദ റേഡിയേഷൻ, ഇൻസിഡന്റ് റേഡിയേഷൻ ടു ഇജക്ട് ഇലക്ട്രോൺ ഫ്രം എ മെറ്റൽ സർഫസ്. ഇസ്മായിൽ ഇല്ലേ? ഇസ്മായിൽ പറയൂ. വാട്ട് ഈസ് ദ ഫോർമുല ടു ഫൈൻഡ് ദ മിനിമം എനർജി ഓഫ് ദ ഇൻസിഡന്റ് റേഡിയേഷൻ ടു ഇജക്ട് ഇലക്ട്രോൺ? h nu ഈക്വൽ ടു h nu. അപ്പൊ ന്യൂ 0 എന്ന് എടുക്കണം, ന്യൂ സഫിക്സ് 0 എടുക്കണം, കാരണം ത്രഷോൾഡ് ആയതുകൊണ്ട്. ത്രഷോൾഡ് എനർജി ചോദിക്കുമ്പോൾ h nu 0 പറയണം. അത് വെറുതെ എനർജി ഓഫ് ദ റേഡിയേഷൻ എന്ന് പറയുമ്പോൾ h nu എന്ന് പറയാം. ഓക്കെ, മിനിമം എനർജി എന്ന് പറയുമ്പോൾ h nu 0. ഇസ്മായിൽ തന്നെ പറയണം അടുത്ത ആൻസർ. വാട്ട് ഇസ് ദ റിലേഷൻ ബിറ്റ്വീൻ ദിസ് h nu 0 ആൻഡ് വർക്ക് ഫംഗ്ഷൻ? Are they equal? Are they different? Is anyone greater than the other? h nu 0 and w 0. Tell. Options are given to you.
Equal, teacher.
Equal, correct. So when the work function is the minimum energy required to eject an electron from a metal surface, and threshold energy means the minimum energy required for the radiation to eject electron from the surface. Both are equal. So W0 equal to h nu 0. Okay. And such radiations are incident, and so what you have to say? When light of frequency greater than the threshold frequency, or you can tell light of frequency, suitable frequency, you can tell. When light of suitable frequency are incident on a metal surface, electrons are emitted from it. So that must be suitable to that particular metal. The light of suitable frequency is incident on a metal surface, it will eject electron. Then that electrons are called photoelectrons, and that current produced. So when electrons move here, that movement of electron, that is current. That is photoelectric current. That current moved to this plate, because why they moved to this plate? Because A is connected to positive of the battery. Positive battery. So all the electrons are attracted, accelerated by this positive plate. Understand? Electrons are negatively charged. This is connected to positive of the battery. So all the electrons are accelerated to this. So when electrons move in particular direction, that produces current, and that is photoelectric current. So photoelectric current is produced now. And how will you read that? If you connect an ammeter, microamperes we are getting. If you connect an ammeter in the circuit, we can read that current. If there is no light, if the light is not incident, will it read any value in this ammeter? No, because no electrons are there. It is completely vacant here. No motion of charges here. The path is incomplete, open, so no current will be there. So just when we show the light, when the light is incident on this plate, light of suitable frequency is incident on this plate, electrons are ejected, and that will move to the plate A, and the current we can read in the ammeter, and that is photoelectric current. Don't think it is the current from the battery. If it is current from the battery, just when we connect it, we should get it reading, but we are not getting the reading. Just when we show the light of suitable frequency, then only electrons are rejected, then only the current starts flowing through this wire and we get that current. That is the photoelectric current. Okay, I'll start the video. So here, next what we can see.
So who discovered photoelectric? In 1887, Henry Purcell saw that light falls on the surface. Some electrons near the surface absorb Earth's energy and incident radiation to earth positive ions in the area of the surface. After gaining sufficient energy from the incident light, electrons escape from the surface of the planet to the space. So that's how Earth observed during his studies, and later two scientists repeat this study.
Between the years of 1886 to 1902, experiments were done by William Hallwatch and Philip Lenard to show light has energy and electrons were ejected from the plates. By that time, they were thinking about light having a material nature, and small packets of energy called photons are emitted by the light. So first, Lenard made an experiment where he allowed the UV rays to fall on the emitter plate C of an evacuated glass tube as shown in the figure, where the current flows in the circuit. But also, as soon as the UV radiation was stopped, current flow also stopped. From this, he observed that the electrons are emitted by the emitter plate C and is collected by the collector plate A. This flow of electrons from the plates resulted in the flow of current in the circuit. Later, Hallwatch continued his studies on this and he connected a negatively charged zinc plate to an electroscope. In that, he observed that the negatively charged zinc plate lost its charge when it was illuminated by the UV light, and also the same uncharged zinc plate became positively charged when it was irradiated by the UV light. From this observation, he concluded that the negatively charged particles were emitted from the zinc plate under the action of UV light. They also observed that no electrons were emitted at all if the frequency of the incident light was smaller than a certain minimum value called the threshold frequency. Photosensitive substances such as metals having short wavelength, for example, zinc, cadmium, magnesium, and some alkali metals such as lithium, sodium, potassium, responded only to the ultraviolet light. After the discovery of electrons, these electrons were termed as photoelectrons, and this phenomena is called photoelectric effect.
Experimental study of photoelectric effect. The figure depicts a schematic view of the arrangement used for the experimental study of the photoelectric effect. It consists of an evacuated glass or quartz tube having a photosensitive plate C and a metal plate A. A transparent quartz window is sealed onto the glass tube, which permits ultraviolet radiation to pass through it. Monochromatic light from the source S fall on C through the window. The electrons are emitted and are collected by plate A by the electric field created by the battery. The polarity of C and A can be reversed by a commutator. When A is positive with respect to C, the electrons are attracted to it. Emission of electrons causes an electric current. The potential difference between C and A is measured by a voltmeter, and the resulting photocurrent is measured by a micrometer. We can use this arrangement to study variation of photocurrent with intensity of radiation, frequency of incident radiation, the potential difference between plates A and C, and the nature of the material of plate C.
Effective intensity of light on photocurrent. The photocurrent is directly proportional to the number of photoelectrons emitted per second. This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation.
This is the experimental study. So here you can see the graph, very important. All these graphs very important. So from the experimental setup, see intensity of light is increased. What's meant by, you have seen that experiment when light is incident on the metal plate, electrons are emitted. Then how will you increase the intensity of light? That you have seen a torch there. And how will you increase the intensity of light? See, if the light source is, when we are standing near to a source of light, very high intensity of light comes. When the light is far from us, intensity of light will be less. So you can make the intensity less or more. One method is that by moving it, taking it closer, intensity increases, taking away from it, the intensity decreases. So like that, if you increase the intensity of light, what happens to photoelectric current? Increase the intensity of light. If you increase the intensity of light, what happens? What is light? Light consists of. Yes.
Admit Ashley.
Okay. So if we increase the intensity of light, means more photons will be incident. Intensity increases, more photons per second will be incident. Then what happens? More electrons will be ejected. More photons are incident, more electrons are ejected per second. That means more photon current is produced. So what happened? When the intensity of the incident light is increased, what happened? Aditya, Mara, when intensity of light increases, what happened to photoelectric current?
More photons per second.
Therefore, photoelectric current.
More electrons ejected.
Therefore,
photoelectric current. So current increases.
Correct. Current increases. Photoelectric current increases. That graph is shown there. This is that graph. When intensity of light is increased, photoelectric current increases. So that is the explanation of this. Photoelectric current is directly proportional to number of photoelectrons emitted per second. This implies that number of photoelectrons emitted per second is directly proportional to intensity of the incident radiation. Clear? Any doubt in this? More intensity increases, more photons are incident, and therefore one photon, one electron, like that the electrons are ejected. So more photons are incident, more electrons will be ejected. That means per second. So more electrons per second, that is the current. Electron flowing per second, that is current. So more current flows, photoelectric current. So that is explanation for that. You can say next.
This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation.
Effect of potential on photoelectric current. We first put the plate A at the positive potential with respect to the plate C with light of fixed frequency. Potential difference between plates A and
I will explain that, then you can hear that. Okay? See, effect of potential. Next. See, here A is connected to this voltage, we can vary with this commutator. This is commutator. That means by rotating this, we can make the contact changing. So, potential, suppose initially A is made positive. Initially A is made positive. So, you have to rotate this. So, this will come in contact with the positive and the other will come in contact with the negative. Initially A is made positive and for example, 5 volt is given, 5 volt plus 5 and this is minus 5, like that. Potential difference is applied. and then at that time we got photoelectric current. Okay, then next we again increases 5 to 10 volt. We are increasing the potential of the plate A with respect to C, 10 volt ആക്കി. അപ്പോൾ വീണ്ടും ഫോട്ടോ ഇലക്ട്രിക് കറണ്ട് കൂടി, all they are accelerated, all the electrons are accelerated, so number of electrons per second increases, so photoelectric current increases. So what we have done, we increase the positive potential with respect to the plate C. This is emitter plate, this is collector plate, this is collecting all the electrons. So we increase the positive potential of A. When we increase the positive potential of A, what happened? Number of electrons reaching per second increases, photoelectric current increases. And do you think that on increasing more and more, the potential will increase? That means indefinitely. Is it indefinite? Or there is a saturation value? Will it be there? What is your opinion when we increase the positive potential? Vishal, what is your opinion? Initially, we have seen there is an increase in current, photoelectric current. So, is it by increasing the potential, will the current again increases, or will there be a saturation value? What is your opinion? Vishal is there?
What is it?
What is your opinion? Indefinitely it will go on increasing, or will there be a saturation value? What is your opinion?
I think go on increasing.
Go on increasing.
Saturation value, teacher.
Saturation
value.
Correct. That is correct. So there is a limit for that. It will first you can see when we increase the positive potential of A, the current will increases, but you know there is a saturation current. Photoelectric current becomes a maximum value, and then further increasing the positive potential, there will be no change. It attains a saturation value. Then you can hear that. So that
MC and the nature of the material of plate C.
You can hear it.
Intensity of light on photocurrent. The photocurrent
This maximum value of photoelectric current is saturation current. Then, if we apply a negative potential to the plate, the photocurrent decreases. At a certain potential, it drops to zero. This is called as stopping potential. It is defined as the potential.
Again, that experiment research that you have to see. Yes, you see. So I told you when we increase the positive potential of this plate A, initially you can see an increase in photoelectric current, and it attains a maximum value that is known as saturation current, maximum value of photoelectric current. Further increasing the potential, there is no change in the photoelectric current. So we do another thing. Increasing is over. Next, we decrease. We try to decrease the potential, lower the potential. That means it is 10, again change it to 5 plus 5, again change it to plus 3, again plus 2, like that reduce. With respect to this plate, this potential 2 volt, 1 volt, 0 volt, like that we reduce the potential and negative voltages. Okay. See, when the positive potential, first it was 10, after that time maximum attained. Then it is 5, reduce photoelectric current. Then it is 2, again reduce photoelectric current. 1 volt reduced, 0, still some electrons were there. But you know, when we reverse the potential, reverse means when A is made negative, will any electron reach here? I'll ask you, Akshaya, when the potential is reversed and made A made negative, will electrons reach here? Akshaya is there? Saliha? Remisa? ഒരെണ്ണം ഉണ്ടല്ല. സിമ്പിൾ ആയിട്ടൊരു ക്വസ്റ്റ്യൻ ആണ് ചോദിച്ചത്. സൽമ ഇസ് ദർ? സൽമ അറ്റൻഡൻസ് നോക്കുമ്പോൾ ഉണ്ടാവും. ഇപ്പൊ ചോദ്യം ചോദിക്കുമ്പോൾ ആരുമില്ല. അഭിനന്ദ്, tell Abhinand, when the potential of A is made negative, will electrons reach here?
teacher.
Huh?
No, teacher.
No, because electrons are negatively charged. And when A is made negative, electrons will not reach. Yeah, they will be repelled. So electrons will not reach there. That means electron will be stopped. Electron will not reach means they will be stopped there. Light is incident. Electrons are rejected. But because of this negative potential, the electrons remains there inside. So that potential is known as stopping potential. So the potential applied, reverse potential applied, the minimum reverse potential applied to stop the ejected electrons. That is known as reverse potential or stopping potential. V0 is stopping potential. So what is stopping potential? The minimum negative potential applied to stop the ejected electron from the metal surface. Stop. It is known as stopping potential. Okay.
Saturate. If we further increase the positive potential state, the photocurrent will change. This maximum value of photoelectric current is called saturation current. Then, if we apply a negative potential to the plate A, the photocurrent decreases. At a certain potential, it drops to zero. This is called as stopping potential. It is defined as the potential at which the photocurrent just becomes zero. The maximum kinetic energy is Kmax equal to V into V naught, where V naught is the stopping potential. For a given frequency of the incident radiation, the stopping potential is independent of its intensity. The maximum kinetic energy Kmax of photoelectron depends only on the light source and the emitted rate T, but is independent of intensity.
That point I will explain. Okay. Here you can see a graph, and here intensity is different. I1, I2, I3, three intensities. But frequency of the radiation is the same source is used, but intensity made when it is made very closer, intensity is more, like that. So intensity is increased. I1, I2, I3, I3 is having maximum intensity. So first we study with the intensity I1. Then with that, now the reverse potential needed is V0. V0 is the negative potential. This is positive potential this side, and this is the negative potential left side. This is the origin, and here we get the photoelectric current. So for the first we studied with the intensity I1. What we do? We reverse the potential to make the photoelectric current 0. Then we got a potential by applying a potential V0 minus V0. All the photoelectrons electrons ejected were stopped. That is the stopping potential. We got V0 for the intensity I1. We got the stopping potential minus V0, and then we increase the intensity. Intensity is increased. Same source. We are not changing the source. The same source intensity is increased. Then what you see? Stopping potential required is same. Again increase the intensity. Then also we can see the stopping potential required to stop the electron. That remains same. Yes.
Aishwarya.
Aishwarya. So what we have seen? We are not changing the source. We are not changing the frequency. What is changing? Only intensity is changing. By increasing the intensity, photoelectric current is increasing. See, I1 this much, I2 this much, I3 this much. Photoelectric current is increasing. But the stopping potential required to stop the electron, that remains same. So, what's the meaning of that? Intensity has no effect in the stopping potential or kinetic energy of the electron. Intensity have no effect on it. Then which is having the effect? Frequency of the incident radiation. So frequency and kinetic energy are related. It is not depending on the intensity. Kinetic energy is related with the kinetic energy of the electron. Electrons are accelerated. Kinetic energy of the electron depends only on the frequency of the incident radiation. It is independent on the intensity of the incident radiation. For a given frequency, source for a given frequency of the incident radiation, the stopping potential is independent of its intensity. Stopping potential is independent of its intensity. The maximum kinetic energy of the photoelectron depends only on the source. That means same frequency, only on the frequency. And the emitter plate material, but independent of intensity. So this is a very important point. Maximum kinetic energy of the photoelectron depends on what? Maximum kinetic energy of the photoelectron depends on intensity or frequency. Arunjit? Kinetic energy of photoelectron, electrons. Kinetic energy of the kinetic energy of the electron emitted depends on what? Intensity or frequency?
Frequency.
Very good. Frequency. It will do
Frequency.
Correct answer. Good. So kinetic energy of the electron depends on the frequency of the incident radiation. Stopping potential also depends on the frequency. It do not depend upon intensity. Okay. Okay. Only 5 minutes.